Hello friends, today we are going to learn about the topic OpenStack Cloud Basic Architecture, what the basic architecture is, the conceptual and the logical architecture, and its design and the use cases in OpenStack Cloud Architecture. OpenStack Cloud Architecture, basic architecture, design and use cases. First of all, for the basic architecture, we should know what is the concept behind that particular architecture. Thus, to know that, we should know what is the conceptual architecture of OpenStack. So, for conceptual architecture, we have this. See, here are some of the components, as we have studied before, the components of OpenStack architecture. So we have these components, that is Glance, Nova, Swift, Cinder, Trove, Neutron, Ironic, Heat, etc. So what these components do, they interact with the virtual machines and then they provide a particular, like what we want, this keystone, celliometer, horizon. It provides the user interface. It will provide, as in concept, it is designed that it should provide, or it will provide the user interface. Then celliometer, it will monitor. Then this keystone, it will provide the authentication. After that, when we come here, there are these Hadoop architecture. We will be using it in the OpenStack Cloud architecture. It is in the concept that Hadoop concept will also be implemented while we are in the basic architecture or basic design of OpenStack. Then we have these components of OpenStack and how these components will interact. It will provide images, or it will boot the databases instances, how it is going to do or how it is going to work, and it will be designed, actually will be in this particular conceptual architecture. Now, after the conceptual architecture, we come across the logical architecture. That means that architecture that can come into the existence, and the design or the particular structure or infrastructure will be upon that logical architecture, or it will be built accordingly, because concepts are first finalized and after that the logical architecture is being designed and then the actual physical infrastructure is implemented. So now the logical architecture. To design, deploy and configure OpenStack, administrators must understand the logical architecture. Now, to design and deploy, that means designing that complete whole framework and then how it can be deployed or it can be functional, it will be working, and then configure. Now we want to deploy it. To deploy it, we need to configure that particular thing or object or infrastructure, and how it will work, what will be the administrators in that, or how the administration of that architecture will work. We have to understand that, and it will be possible with the help of this logical architecture. Now, as shown in conceptual architecture, OpenStack, it contains or it consists of several independent parts. As we have seen in the conceptual architecture, there will be a lot of independent parts. So, named the OpenStack services. How these independent parts will work? It will be as and in form of services in the conceptual architecture. Now, all services authenticate through a common identity, as we have seen in the diagram. Then individual services interact with each other through public APIs, that is application programming interfaces, except where privileged administrator commands are necessary. Then internally, OpenStack services are composed of several processes. All services have at least one API process. That means to run or to execute themselves, they should have at least one of the application programming interfaces process in it, which listens for the API request, pre-processes them and passes them on the other parts of the service. With the exception of the identity service, the actual work is done by distinct processes. Then for communication between the processes of one service, an AMQP message broker is used because this message broker will provide the packets to pass between those services. The services state is stored in the database. When deploying and configuring the Openstack cloud, here you can choose among several message brokers. That means for several services we can have several message brokers to send the packets from one place to another, or for the communication between those services. And database solutions such as RabbitMQ, MySQL, MariaDB and SQLite. Then users can access Openstack via the web-based user interface implemented by the Horizon dashboard via command line clients and by issuing API requests through tools like browser plugins or curl. For application, several SDKs, that means software development kits, are available. Ultimately, all these access methods is issue, that is REST API calls. That means whatever the services are there or whatever the access methods we are using in that architecture for implementation, they will be using this or issuing REST API, that is REST API calls to various OpenStack services. Now there is a diagram which will show the most common but not the only possible architecture for an OpenStack cloud. That means we are looking for a diagram, but it will not be the only one which will represent the OpenStack cloud. There can be several other variations for that particular infrastructure or deployment model or the configuration. Now this is the diagram. See, as we all know, first we have this OpenStack bare metal service. Then we have OpenStack orchestration, OpenStack dashboard, OpenStack identity service, this OpenStack telemetry, OpenStack data processing, OpenStack networking, OpenStack image service, OpenStack block storage. Now the type of storage which OpenStack will be using. Then OpenStack compute, OpenStack database service and OpenStack object storage. So basically two types of storage are mentioned here. That is, first one is block storage and the other one is object storage in logical architecture. Now, when we go for OpenStack object storage, here we have this accounts database, object database and container database. Then these are connected to Swift object server, Swift account server and Swift container server. Then they combine and form this Swift proxy server. Now, coming back to OpenStack database services. Database services, it is connected or it comprises of Trove conductor, Trove task manager, Trove database queue and then this Trove API. So when we are going to this database services, we will be interacting with Trove API to get into this thing. Then we come here for OpenStack compute. Here it is comprised of or it comprises of components of OpenStack, which is Nova API, Nova scheduler, Nova console, Nova database, Nova conductor, guest agent, Nova consolute, Nova cert, Nova compute and then the hypervisor. Then we are coming to the another type of storage which is an OpenStack logical architecture. This is this block storage. Now block storage comprises of, as we have seen in object storage, there to interact with the object storage we have to go through this Swift API or Swift proxy API. Here we have this Cinder database, Cinder volume, volume provider and Cinder scheduler. So to interact with this block storage, you have to go through this Cinder API and then you can go through the everything or the database which is there or the storage architecture which is being provided in OpenStack. So there are two type of storage architecture provided in OpenStack. That is, one is block storage and another one is object storage. All two of them are different from each other. One is uses Cinder API and another one uses Swift Proxy API server. Then coming back to OpenStack image services, how it will work, it will be interacted through, or we can get through it by Glance API. So it comprises of Glance store, Glance database, Glance registry. Then coming to OpenStack networking. For OpenStack networking, we have this to interact or to get through it, we should interact with this Neutron server. Then it has this Neutron agent and then Neutron DHCP, Neutron database and party plugin. Then with this OpenStack data processing, it comprises of Sahara database, Sahara ALL, and the architecture in this is the queue. That means when you interact with the data processing, it will be in the queue. As we all have studied in the earlier or basic things, we know what is a queue, what is a linked list. So here it is in the form of queue. Then coming back to OpenStack telemetry, so to get through it, the API used here is Celiometry API, and it has the Celiometry collector, Celiometry database, Celiometry agent notification, agent compute, Celiometry agent central, then alarm evaluator and alarm notifier. Then coming to the OpenStack identity stack, to interact with this, we should know, or we have to get through Keystone ALL. Then to interact with OpenStack identity service, we have to get through it with Keystone ALL. It comprises of LDAP database and the optional creator, that means the optional option in this. Then we have this OpenStack orchestration. Now to get into this, the API used here is Heat API, and then Heat Engine and Heat API CFN. Then OpenStack dashboard, it uses Horizon. As we all know, in conceptual architecture, we have seen Horizon will be providing the user interface to the clients or the end user who is using it, the OpenStack cloud. And after that, we have this OpenStack bare metal. As we all know what bare metal is, it is a type of virtualization technique or type of hypervisor. It is type 1 hypervisor. So here, this is Ironic conductor, Ironic database, drivers, and then to interact with this, the API used here is Ironic API. Now, the design. Designing an OpenStack cloud requires an understanding of the cloud users' requirements and needs to determine the best possible configuration. Here, it provides guidance on the decisions you need to make during the design processes. To design, deploy, and configure OpenStack, administrators must understand the logical architecture, as we have seen in the previous diagram. That means what all things are present there, how you can get into that particular section of the cloud, and the accessibility is provided, how services communicate with each other, how you can access. That means to access any of the particular issue or the service, you have to issue, or the services have to issue REST API, and then only they can communicate or request for the other APIs. So we have to understand this logical architecture. Then OpenStack modules are one of the following types we are going to learn. First one is daemon. Runs a background process on Linux platforms. A daemon is usually installed as a service. Then second one is script. Installs a virtual environment and runs test. Then another one is command line interface, enables users to submit API calls to OpenStack services through commands. Now, Openstack logical architecture shows one example of the most common integrated services with Openstack and how they interact with each other. That means those services, how they interact with each other to form one cloud service required by the end user, for which it is deploying that particular cloud services or going to that Openstack cloud architecture. End users can interact through the dashboard, CLIs and APIs. All services authenticate through a common identity service, as we have seen in the logical architecture, and individual services interact with each other through public APIs, except where privileged administrator commands are necessary. Then this is the another diagram which shows how it works. See, as we all know, OpenStack identity API, then OpenStack identity service, it includes token, backend, catalog, policy, identity, and then this is the keystone. As we have seen in the conceptual architecture, there was the keystone. Now we can relate to it here, that conceptual, there are some things in the concept which is implemented or concept is being made to be implemented there. Then we have this Nova database, or I could say the OpenStack compute, where all these components combine and perform the compute operations. Then we have this OpenStack image services, which is done with this glance database. And then we have the object store, where you have account databases, container databases, object databases, and how it is accessed or availed with the Swift proxy server. These are the users who are accessing it with this internet, and how this internet connects with the OpenStack architecture or the cloud is, first of all, it will send some secure instructions, HTTPS, via HTTPS protocol to the Horizon. Horizon provides user interface. Then it deals with the OpenStack dashboard. Then OpenStack image API, it deals with glance database. Then OpenStack object API, again this is object API, and the previous one which interacts with glance database is image API. So object API, it interacts with the Swift proxy to access. Then OpenStack compute API, it deals with the Nova API. These are all public APIs which is being issued and then accessed, or you could say the desired request is being accessed or processes are being performed with these APIs. Then we have this VNC VMRC, which interacts with that Nova console directly. Usually these services, see here, as we have mentioned, this Amazon Web Service EC2 uses API, and this can conduct the services or communicate between those services and access it. Then OpenStack Networking API, or I could say the block storage API, it communicates with Cinder API, as we have seen in the logical architecture. Then we have this OpenStack Networking API with Neutron server. It is OpenStack networking, or the networking is provided in the cloud with this networking stack. Now, OpenStack logical architecture explained. Compute architecture. Compute architecture consists of compute server architecture, choosing a CPU, choosing a hypervisor, we have seen in the architecture, then choosing server hardware, overcommitting CPU and RAM, instance storage solutions. What all things this compute architecture is providing? Network connectivity, compute server, logging. Then storage architecture, it provides storage concepts, storage architecture. Network architecture, networking concepts, designing an OpenStack network and additional networking services. Identity architecture, and then image service architecture. Then we have this control plane architecture, which has hardware consideration, separation of services, database, message queues, conductor services, application programming interfaces, extensions, scheduling, images, dashboard, authentication and authorization, network considerations. Then we have this cloud management architecture. It has technical details of the cloud in which we are working or which we will be working, the configuration, capacity and scale, high availability, operator requirements, deployment consideration, maintenance considerations. Then we have this compute server architecture, which we have known that there will be in the logical architecture. So what is there in compute architecture? When designing compute resource pools, consider the number of processors, amount of memory, network requirements, the quantity of storage required for each hypervisor, and any requirement for bare metal hosts provisioned through Ironic. Then, when architecting an OpenStack cloud as part of the planning process, here you must not only determine what hardware to utilize, but whether compute resources will be provided in a single pool or in multiple pools or availability zones. Here, you should consider it if the cloud will provide distinctly different profiles for the compute architecture or compute processes, compute services. Then, for example, CPU, memory, or local storage based computer nodes or compute nodes. For NFV or HPC based clouds, there may even be specific network configurations that should be reserved for those specific workloads on specific compute nodes. Then, this method of designing specific resources into group or zones of compute can be referred to as bin packing. That means the designing technique which we are studying is known as bin packing. That means we are compacting it or creating zones or groups of these particular services. That means this type of services will be in this group or this zone, then another type of service which are likely related to each other, then they will be in another group or another zone. So they are all bins. We are creating all the bins in their packages because they give a lot of service to other services or to the end users, so they are known as bin packaging. Then, increasing the size of supporting compute environment, it increases the network traffic and messages, adding load to the controllers and administrative services used to support the OpenStack cloud or networking nodes. When considering hardware for controller nodes, whether using the monolithic controller design where all of the controller services live on one or more physical hardware nodes, or in any of the newer shared nothing control plane models, adequate resources must be allocated and scaled to meet the scale requirement. That means if the requirement for some resources arrives, and now with this they need every month they need to increase their particular requirement, so it should be allocated to them and the scaled level should be provided to them. So in that way we have to consider these particular requirements or architecture design. Then, effective monitoring of the environment will help the capacity decisions on scaling. Proper planning will help avoid bottlenecks and network oversubscription as the cloud scales. Compute nodes automatically attach to OpenStack clouds, resulting in a horizontally scaling process when adding extra compute capacity to an OpenStack cloud. To further group compute nodes and place nodes into appropriate availability zones and host aggregates, additional work is required. It is necessary to plan rack capacity. Rack capacity, as we all know, when we manage the data center, we keep those storages in racks. That is the rack capacity, and network switches as scaling out compute hosts directly affect data center infrastructure resources as would any other infrastructure expansion. That means, see, in data center we have those racks in which that hardware or storage devices are kept. So that scaling, it will affect the storage or data center more directly as compared to the other expansions which will be provided through cloud computing. Then, while not as common in large enterprises, compute host components can also be upgraded to account for increases in demand known as vertical scaling. Upgrading CPUs with more cores or increasing the overall server memory can add extra needed capacity depending on whether the running applications are more CPU intensive or memory intensive. We recommend a rolling upgrade. So here, when in OpenStack cloud architecture, a rolling upgrade is recommended of compute nodes for redundancy and availability. Redundancy, we all know, multiple copies of the same data, and availability, that means availability of data or information whenever the client requires it for the business continuity. After the upgrade, when compute nodes return to the OpenStack cluster, they will be re-scanned and the new resources will be discovered, adjusted in the OpenStack database. When selecting a processor, compare features and performance characteristics. Some processors include features specific to virtualized compute hosts such as hardware-assisted virtualization and technology related to memory paging, also known as EPT, shadowing in cloud computing. These type of features can have a significant impact on the performance of the virtual machine. The number of processor cores and threads impacts the number of worker threads which can be run on a resource code. Design decisions must be, or it must relate directly to the service being run on it, as well as provide a balanced infrastructure for all the services which is there in the architecture, or which we comprise in the design of the OpenStack cloud. Then another option is to assess the average workloads and increase the number of instances. Instances will be increased with the glance databases that can run within the compute environment by adjusting the overcommit ratio. This ratio is configurable for CPU, that means the processing unit, and the memory in which it is working. The default CPU overcommit ratio is 16:1 and the default memory overcommit ratio is 15 or 1.5:1. Determining the tuning of overcommit ratios during the design phase is important as it has a direct impact on the hardware layout of the compute nodes. Insufficient disk capacity could have a negative effect on overall performance, including CPU and memory usage. Depending on the back-end architecture of the OpenStack block storage layer, capacity includes adding disk shelves to enterprise storage systems or installing additional block storage nodes. Upgrading directly attached storage installed in compute host and adding capacity to shared storage for additional ephemeral storage to instances, then it may be necessary. Now here, considering the compute requirements of non-hypervisor nodes, also referred to as the resource nodes because they will be the physical resource providers node. Hypervisor nodes are the virtualization nodes. So this includes controller, object storage nodes, block storage nodes, and networking services, because these are the actual resources is being provided in the cloud computing services. The ability to create pools or availability zones for unpredictable workloads should be considered. In some cases, the demand for certain instance types or flavors may not justify individual hardware design. Allocate hardware designs that are capable of servicing the most common instance requests. Here, heading hardware to overall architecture, that can be, see, we can learn about it, how we will add the hardware into the architecture, that will be later on or in later phases. Now, the storage concepts. Storage is found in many parts of Openstack cloud environment. As we all know, we have seen the conceptual and logical architecture of it. It is important to understand the distinction between ephemeral storage and persistent storage. What is ephemeral storage here? If you only deploy Openstack compute services, that means the Nova component, by default users do not have access, or by we can default the users or the users who will be using that storage, that they do not have access to any form of persistent storage. The disk associated with virtual machines are ephemeral, meaning that from the user's point of view, they disappear when a virtual machine is terminated. Now here we can see what ephemeral means. Ephemeral means, that means the disk which are associated with the virtual machines. Now they are associated with the virtual machine. Say for example, the user is working in this particular storage. So as per the user's point of view, what will happen? The view, that means it will disappear as soon as virtual machine is terminated. That means it will no longer be available to the user. Then persistent storage. Persistent storage means that the storage resources outlives any other resource and is always available regardless of the state of running instance. That means it will be there either the machine is running or is terminated. Openstack clouds explicitly support three types of storage or persistent storage, we would say: object storage, block storage, and file-based storage. Now, coming to the type of persistent storage. First one, object storage. Object storage is implemented in Openstack by the object storage service, which is Swift, as we have seen in the logical architecture diagram and conceptual architecture diagram as well, that this Swift proxy server, it helps with the API to interact with the Openstack object storage or to get through it. Then users access binary objects through a REST API, that is REST API. We know that it issues this particular API to access or to get into the services. If the intended users need to archive or manage large data sets, you should provide them with object storage service. Additional benefits with this object storage includes: first one is Openstack can store the virtual machine images inside an object storage system as an alternative to the storing the images on a file system. Integration with Openstack identity and works with the Openstack dashboard. Now this object storage, it integrates with the Openstack identity services and also it works well with the Openstack dashboard. Better support for distributed deployments across multiple data centers through support for asynchronous eventual consistency replication. Then here, while in Openstack Cloud, you should consider using the Openstack Object Storage Service if you eventually plan on distributing your storage cluster across multiple data centers. If You need unified accounts for your users for both compute and object storage, or if you want to control your object storage with the OpenStack dashboard, or you could say it is provided, or the services is provided with the user interfaces. Horizon provides that user interface, and it is with this OpenStack dashboard, and then you can control your OpenStack or object storage with this user interface. Then comes block storage. Block storage is implemented in OpenStack by the block storage service Cinder. We have seen that in the architectural diagram. Then, because these volumes are persistent, they can be detached from one instance and reattached to another instance, and the data in that it remains intact. So this is why block storage is being used more prominently in the cloud architectures. The block storage service supports multiple backends. That means it not only work for one backend, it can work for multiple backends there in the form of drivers. Here, your choice of a storage backend must be supported by a block storage driver. Most block storage drivers allow the instance to have direct access to the underlying storage hardware's block device. This helps increase the overall read-write input-output. However, support for utilizing files as volumes is also well established with full support for NFS, that means the file system, cluster file system, and others. These drivers work a little differently than a traditional block storage driver. On an NFS or cluster file system, a single file is created and then mapped. That means you create a file once and then you map it. Map it as a virtual volume because it is not physically existing. So you are mapping it as a virtual volume into the instance. This mapping and translation is similar to how OpenStack utilizes QEMU's file-based virtual machines stored in that library which is present there. We can see it from this example. Then file-based storage in persistent storage. In multi-tenant OpenStack cloud environment, multi-tenant, we all know that simultaneously clients use that particular architecture at a time and rent the services. The shared file system service provides a set of services for management of shared file services. The shared file system service supports multiple backends in the form of drivers and can be configured to provision shares from one or more backends. Shared servers are virtual machines that export file shares using different file system protocols such as NFS, CIFS, clusterFS, that means file systems, or HDFS. Here, the shared file system service is persistent storage and can be mounted to any number of client machines. It can also be detached from one instance and attached to another instance without data loss. During this process, the data are safe unless the shared file system services itself is changed or removed. Here, the users interact with the shared file system services by mounting remote file systems on their instances with the following usage of those systems for file storing and exchange. The shared file system services, it provides shares which is remote mountable file system. That means it can be mounted over some of the devices or the files and then you can access it or run it. Here, you can mount a share and access a share from several hosts. That means you can mount that particular shared file and you can access that share file from several hosts by several users at a time. That means simultaneously they can do the same process, multiple users. With shares, you can also, now share also provides some of the other services, which are create a share specifying its size, shared file system protocol, visibility level. Then you can also create a share on either a share server or a standalone system, depending on the selected backend mode. Now here we all know that there can be multiple backends also where this share works. So depending on the selected backend mode, with or without using a share network. Again, specify access rules and security services for the existing shares. Here combine several shares in group to keep data consistency inside the groups for the following safe groups operations. Create a snapshot of a selected share or a share group for storing the existing shares consistently, or creating new shares from that snapshot in a consistent way. Here we can create a share from the snapshot, set rate limits and quotas for specific shares and snapshots, then view usage of share resources and remove shares. Now we can see with the help of this table how particular application work in those storage. Ephemeral storage, block storage, object storage and shared file system storage. We are comparing these things or these four storages with the help of this table. First one, application. Application in ephemeral storage run operating system and scratch space. Block storage, additional or add additional persistent storage to a virtual machine. Object storage, in this applications store data including virtual machine images. Shared file system storage, in this applications add additional persistent storage to a virtual machine. Then we are going for the accessing of the services. Then access through, in ephemeral storage it access through a file system. In block storage, a block devices, or it can be accessed through the block devices that can be partitioned, formatted and mounted, such as DEV, VDC, etc. These are the examples of the files which can be partitioned and formatted and mounted. Then again, in object storage, the files can be accessed through the REST API. And then in shared file system storage, the files can be accessed through a shared file system service, which share either it is Manila managed or an external one registered in the Manila, that can be partitioned, formatted and mounted. Now it also has the same example like DEV and VDC. Another format is accessible from ephemeral storage within a virtual machine. Then within a virtual machine, again in the object storage, block storage anywhere, and then shared file system within a virtual machine. Then managed by, again with the storages, we have this Openstack compute in ephemeral, then Openstack block storage Cinder, Openstack object storage Swift, Openstack share file system storage Manila. Then again persists until, in ephemeral storage, virtual machine is terminated. Then deleted by the user, deleted by the user, deleted by the user, in all of the three types of persistent storage. Again, sizing determined by, here administrator configuration of size, settings known as flavors. Then user specification in initial request, amount of available or availability of physical storage. Then user specification in initial request, request for extension, available user level codes and limitations applied. Then encryption configuration in ephemeral storage, parameter in nova.con or COFNF, that is configuration. Then in all the three types of persistent storage, admin establishing encrypted volume type, then user selecting encrypted volume. Then in the next one, not yet available, and the other one, shared file system service does not apply any additional encryption above what the shares backend storage provides. Then again, example of typical usage in ephemeral storage, it is 10 GB first disk, 30 GB second disk. In the types of persistent storage, first type 1 TB disk, second type tens of TBs of dataset storage. Then in the shared file system type, it depends completely on the size of backend storage specified when a share of or share was being created. In case of thin provisioning, it can be partial space reservation. For more details, we can see the capabilities and extra specs specification which is being provided there. Now, the networking concepts in the architecture. A cloud environment fundamentally changes the way that networking is provided and consumed. Understanding the following concepts and decisions is imperative when making architectural decisions. Network zones is the first concept and the decision. Networking zone, the cloud networks are divided into a number of logical zones that support the network traffic flow requirement. It has to be divided in the logical zones to see the traffic flow. That means where the traffic flow is required the most, or where the traffic is the most, and where it is manageable or the least. We recommend defining the least 4 distinct network zones. Then second one is underlay. The underlay zone is defined as the physical network switching infrastructure that connects the storage, compute and control platform that are or there are a large number of potential underlay options available. Then overlay. The overlay zone is defined as any L3 connectivity between the cloud components and could take the form of SDN solutions such as the neutron overlay solution or third-party SDN solutions. See, we have seen this L3 network connection or L3 connectivity in the logical architecture. We can connect it from there. Then the another one is edge. The edge zone is where network traffic transitions from the cloud overlay or SDN networks into the traditional network environment. Then another one is external. Now in external, the external network is defined as the configuration and components that are required to provide access to cloud resources and workloads. The external network is defined as all the components outside the cloud edge gateways. Now the another one in networking concepts is traffic flow. There are two primary types of traffic flow within a cloud infrastructure. The choice of networking technologies is influenced by the expected load. First, east-west. The internal traffic flows between workload within the cloud as well as the traffic flow between the compute nodes and storage nodes falls into the east-west category. Here, generally, this is the heaviest traffic flow, and due to the need to cater for storage access needs to cater for a minimum of hops and low latency. Then the next one is north-south. The flow of traffic between the workload and all external networks, including clients and remote services. This traffic flow is highly dependent on the workload within the cloud and the type of network services being offered. Now comes the layering networking choices or layer networking choices. There are several factors to take into considerations when deciding on whether to use layer 2 networking architecture or layer 3 networking architecture. There is mentioned L2 architecture and L3 architecture in the cloud diagram or the block diagram of the architecture. Benefits of using L2 architecture or layer 2 network. There are several reasons a network designed on layer 2 protocol is selected over a network designed on layer 3 protocols. In spite of the difficulties using a bridge to perform the network role of a router, many vendors, customers and service providers, they choose to use Ethernet as many parts of their network as possible. The benefits of selecting layer 2 or L2 network design are: first one, Ethernet frames, they contains all the essentials for networking. These include but are not limited to globally unique source addresses, globally unique destination addresses and error control. Then the another one or the next benefit is Ethernet frames can carry any kind of packet. Networking at L2 or layer 2 is independent of the layer 3 protocol or L3 protocol if both of them are working simultaneously there. Adding more layers to the Ethernet frame only slows the networking process down. This is known as nodal processing delay. Then here you can add adjunct network features or networking features. For example, class of service COS or multicasting to Ethernet as readily as IP networks, and virtual LANs, that is virtual local area networks, are an easy mechanism for isolating networks. That means within the LAN we can create several other VLANs so that we can isolate the network and traffic flows easily. Most information, it starts and ends inside Ethernet frames. Today, this applies to data, voice and video. See, we are more like we access several data applications, we access the web pages through data, or information is transferred and received, then voice messages, voice calling and video messages, video callings, etc. This comes or this applies to these types of data transfer. The concept is that the network will benefit more from the advantages of Ethernet if the transfer of information from a source to a destination is in the form of Ethernet frames. Although it is not a substitute for IP networking, that is Internet Protocol networking, a networking at L2, that is layer 2, can be powerful adjunct to the IP networking. Layer 2 Ethernet usage has additional benefits over layer 3 IP network usage. That means if you are using layer 3, it has more addition or additional benefits to that. Then speed, reduced overhead of IP hierarchy, no need to keep track of address configuration as system moves around. Whereas the simplicity of L2 protocols might work well in data center with hundreds of physical machines, cloud data centers have the additional burden of needing to keep track of all the virtual machines, addresses and networks. In these data centers, it is not uncommon for one physical node to support 30 to 40 instances. Then layer 2 architecture limitations. Layer 2 network architectures have some limitations that become noticeable when used outside of traditional data centers. That means when number of virtual LANs is limited to 4096, the number of MACs, that is MAC addresses stored in switch tables, is limited. That means it can be countable. Then you must accommodate the need to maintain a set of layer 4 device to handle traffic control, MLAG, often used for switch redundancy, is proprietary solution that does not scale beyond two devices and forces vendor lock-in. These are all the limitations for that particular L2 network architecture. It can be difficult to troubleshoot a network without IP addresses and ICMP. Configuring ARP can be complicated on a large L2 networks. All network devices need to be aware of all MAC addresses or MACs, that is medium access control, even instance MACs or instance MACs. So there is constant churn in MAC tables and network state changes as instances start and stop. Migrating MACs, that is instance migration, to different physical locations are a potential problem if you do not set ARP table timeouts properly. Here it is important to know that L2 has a very limited set of network management tools. It is difficult to control traffic as it does not have mechanism to manage the network or shape the traffic. Network troubleshooting is also troublesome, in part because network devices have no IP, that is Internet Protocol, addresses. As a result, there is no reasonable way to check network delay or why a network packet is not being delivered to the destination at the scheduled time. In L2 network or layer 2 network, all devices are aware of all MACs. Even those that belong to instances, the network state information in the backbone changes whenever an instance starts to or stops. Because of this, there is far too much churn in the MAC tables on the backbone switches when we are in the L2 or layer 2 networking architecture. Furthermore, on large layer 2 networks, configuring ARP learning can be complicated because we need to complete it every time. And then the setting for the MAC address timer on switches is critical, and if set incorrectly can cause significant performance problems. So when migrating MACs to different physical locations, to support instance migration, problems may arise. As an example, the Cisco default MAC address timer is extremely long. As such, the network information maintained in the switches could be out of sync or will not be synchronized with the new location of the instance. Benefits of using layer 3 network. In layer 3 networking, routers take instance MAC and IP addresses out of the network core, reducing the state churn which was present there in the layer 2 network architecture. The only time there would be a routing state change is in the case of a top of rack switch failure or a link failure in the backbone itself, which is connecting all of them. Other advantage of using a layer 3 architecture, it includes layer 3 network provides the same level of resiliency and scalability as the internet, and controlling traffic with routing metrics is straightforward. That means it will be there and it is straight. That means you need not to complicate that. It is simple as you do. Then you can configure layer 3 to use border gateway protocol, that is BGP configuration for scalability. This way, core routers have state proportional to the number of racks, not to the number of servers or instances. There are a variety of well-tested tools such as Internet Control Message Protocol ICMP to monitor and manage traffic. Then layer 3 architecture enable the use of quality of service to manage network performance. Then layer 3 architecture limitations. The main limitation of layer 3 networking is that there is no built-in isolation mechanism. That means you need to create one comparable to the virtual LANs in the layer 2 network. That means this isolation mechanism is built in when we are working in layer 2 network using virtual LANs, but in layer 3 we need to create it because there is no built-in isolation mechanism. Furthermore, the hierarchical nature of IP addresses means that an instance is on the same subnet as its physical host, making migration out of the subnet difficult. For these reasons, network virtualization, it needs to use IP encapsulation and software at the end of the host or at the end host. This is for isolation and the separation of the addressing in the virtual layer from the addressing in the physical layer. Other potential disadvantages of layer 3 networking include the need to design an IP addressing scheme rather than relying on the switches to keep track of the MAC addresses automatically, and to configure the interior gateway routing protocol IGMP in the switches. Now, networking service, that is Neutron, which is in the architecture of the open cloud stack. Openstack Networking, Neutron, is the component of Openstack that provides the networking service API and a reference architecture which implements a software-defined network, that is SDN solution. The networking service provides full control over creation of virtual network resources to the tenants. This is often accomplished, or the task which we have been discussing, it is often accomplished in the form of tunneling protocols that establish encapsulated communication paths over existing network infrastructure in order to segment tenant traffic. This method varies depending on the specific implementation, but some of the more common methods include tunneling over GRE, encapsulating with VXLAN, that is VXLAN, and VLAN tags. Now, the use cases in OpenStack Cloud architecture. Development cloud, there are several use cases, some of which we are going to discuss here. The first one is development cloud, second one is general compute cloud, third one web scale cloud, then storage cloud, and then the network virtual function cloud. The general compute cloud, the use case which we are going to discuss in detail is general compute cloud. An online classified advertising committee or company wants to run web application consisting of Tomcat, Nginx, MariaDB in a private cloud. So, to meet the policy requirements, the cloud infrastructure will run their own data center. The company has predictable load requirements but requires scaling to cope with nightly increases in demand. Their current environment does not have the flexibility to align with their goal of running an open source application programming interface environment. The current environment, it consists of the following thing in this cloud. First, between 120 and 140 installation of Nginx and Tomcat, each with 2 vCPUs, that is virtual CPUs, and 4 GB of RAM. A 3-node MariaDB and Galera cluster, each with 4 CPUs, that is virtual CPUs, and 8 GB of RAM. The company runs hardware load balancers and multiple web applications serving their websites and orchestrates environments using combination of scripts and Puppet. The website generates large amounts of log data daily that requires archiving. The solution here would consist of the following Openstack components. First, a firewall, switches and load balancers on the public facing network connections. Then Openstack controller, service running image service, identity service, networking service combined with the support services such as MariaDB, RabbitMQ, configured for high availability on at least 3 controller nodes. Then OpenStack compute nodes running the KVM, that is Kubernetes Virtual Machine Hypervisor. Then OpenStack block storage for use by compute instances requiring persistent storage such as databases for dynamic sets. OpenStack object storage for serving static objects such as images. Running up to 140 web instances and the small number of MariaDB instances requires 292 virtual CPUs available as well as 584 GB of RAM. On a typical IU server, usually dual socket hex core Intel CPUs with hyperthreading and assuming 2:1 CPU overcommit ratio, this would require 8 OpenStack compute nodes. See, we are looking into the scenario or the use case for a company. If it is using a general compute cloud, what will be the requirements, how it will be working. First, we have analyzed what is the requirement of that particular company. Now we are working on how that requirement is going to meet. The web application instances run from local storage on each of the OpenStack compute nodes. Then the web application instances are stateless, meaning that any of the instances can fail and the application will continue to function. MariaDB server instances store their data on shared enterprise storage, such as NetApp or SolidFire devices. If a MariaDB instance fails, storage would be expected to be reattached to another instance and rejoined to the Galera cluster. Logs from the web application servers are shipped to OpenStack object storage for processing and archiving. Additional capabilities can be realized by moving static web content to be served from OpenStack object storage containers and backing the OpenStack image service with OpenStack object storage. Then comes the storage cloud in this scenario. Storage focused architecture depends on specific use cases. This is the another one which we are learning. We have seen general compute cloud. Now this is the storage cloud. An object is stored with RESTful interface, compute analytics with parallel file system, high performance databases. The example REST interface presented as a traditional object store running on traditional spindles does not require a high performance caching tier. The example uses following components here which we are using the example. First one, network. 10 GBE horizontally scalable spine leaf backend storage and front-end network. Then storage hardware, 10 storage servers each with 12 into 4 TB disks equaling 480 TB total space with approximately 160 TB of usable space after replicas. Then proxy, 3x proxies, 2x 10 GBE bounded frontend, 2x 10 GBE backend bonds, approximately 60 GB of total bandwidth to the backend storage cluster. Now, network virtual function cloud. An organization designs a large-scale cloud-based web application. The application scales horizontally in a bursting behavior and generates a high instance count. The application requires an SSL connection to secure data and must not lose connection state to individual servers. The figure below depicts an example design for this workload. In this example, a hardware load balancer provides SSL offload functionality and connects to tenant networks in order to reduce the address consumption there. Here, this particular load balancer, it links to the routing architecture as it services the VIP for the application. The router and load balancer use the GRE tunnel ID of the application's tenant network and an IP address within the tenant subnet but outside the address pool. This is to ensure that the load balancer can communicate with the application's HTTP servers without requiring the consumption of a public IP address. Because sessions persist until closed, the routing and switching architecture provides high availability into that area or the work. Switches mash to each hypervisor and each other and also provide an MLAG implementation to ensure the L2, that is layer 2 connectivity, it does not fail in that scenario. Routers use VRRP and fully mesh with switches to ensure layer 3 connectivity here. So here both L2 and L3 connectivity is present. Since GRE provides an overlay network, networking is present and uses the open switch virtual open vSwitch agent in GRE tunnel mode. This ensures all devices can reach all other devices and that you can create tenant networks for private addressing links to the load balancer. How load balancer work here? See, we have these instances, instance 1, 2 and 3, then up to instance n. This is the tenant private network and tenant overlay network is this. So now these instances, they are connected with switch and switches in a mesh network. Then these switches, they connect to the routers and then it is connected to the load balancer, and this is how this particular scenario works. A web service architecture has many options and optional components. Due to this, it can fit into a large number of other Openstack designs. A few key components, however, need to be in place to handle the nature of most web scale workloads. You require the following components. First one, Openstack controller services. It is image service, identity service. It will provide image service, identity service, networking service and supporting services such as MariaDB and RabbitMQ. Then Openstack compute running KVM hypervisor. Then Openstack object storage, orchestration service, telemetry service. Beyond the normal identity service, compute service, image service and object storage components, here it is recommended that orchestration service component to handle the proper scaling of workload to adjust to the demand of the user or the client. Due to the requirement for auto scaling, the design includes the telemetry services. Web services tend to be bursty in load, have very defined peak and valley usage patterns, and as a result benefit from automatic scaling of instances based upon traffic. At a network level, a split network configuration works well with the databases residing on private tenant networks since these do not emit a large quantity of broadcast traffic and may need to interconnect to some databases for the content. Thank you.